So, as I was saying, it says essentially we all know this though, right? Like, but we have to talk about why. So it says hot body here at Ti over time will lose temperature to the colder body, right? I think everyone kind of knows that this takes place, right? It says in conformity with the conversion of energy principle, the decrease in internal energy of the body appears as an increase in the internal energy of the surroundings. So essentially what it is saying is that as the hot body loses energy, the cold surroundings gain energy, right? At the same time. Okay? It says the inverse process would not take place spontaneously, even though energy could be conserved. The internal energy of the surroundings would not decrease spontaneously while the body warmed from T naught to its initial temperature. So what it is saying is the following, is that if the inverse process took place, it would not be spontaneous. And so they'll talk about spontaneous in a little bit. And so, right here, it says the internal energy of the surroundings would not decrease spontaneously while the body warmed from its low temperature to high. So think about it this way. It's saying that this right here, we can all agree, takes place, all the time, right? We have hot, it goes to cold, and the outside and the heat leaving enters the surrounding area, right? Which is why, as something is sitting around, you know that there's heat around it, right? There is the air around something hot is hot, right? It's losing heat to the air around it. Now, if the reverse took place, so let's say instead of going that way, we went this way, right? We had T naught, which is now the temperature of the atmosphere, so this is also T naught, right? And then we heated it back up. So instead of Q out, we're going to put some heat in, right? What it is saying is that this reverse one does not take place in the same manner, right? The energy of the air around it does not lose and go into here. You see what I'm saying? Does that make a little bit of sense? We'll talk more about this in just a minute, but that's what they're trying to put out as like an initial statement. Now let's look at the next example. So we have spontaneous heat transfer is A. So this is spontaneous heat transfer. B is spontaneous expansion. And then we have a falling mass. So we're going to talk more about these. So we have system B. Air held at a high pressure in P1. So this could be let's just say it's really high pressure, right? In a closed tank flows spontaneously to the lower pressure surroundings at P naught when the interconnecting valve is opened, as illustrated. So we have high pressure. Valve is opened. Now we know that the air inside is now the same as the air outside, right? Would you guys agree? If you've ever, broke open a can, not a can, but like compressed air or something. This is what happens, right? It goes to an equilibrium pressure, right? Which happens to be the outside. And then it says, eventually fluid motions cease and all air is at the same pressure as its surroundings. Drawing on experience, it should be clear that the inverse process would not take place spontaneously, even though energy could be conserved. Air would not flow spontaneously from the surroundings into the tank, right? Returning the pressure from its initial value. So essentially what it's saying is that, you guys know this as well, is that if we did the reverse and went this way, you guys know that there has to be something else happening here. There isn't this part where it goes from valve opened and air just flows out and now we're at the same pressure. This cannot happen in reverse where air is out here and now it's back in at the high pressure, right? Would you guys agree with that? Like, it doesn't work the reverse way. That's what I'm trying to get at. It does not work the reverse way, right? And so this is where we're getting into the second law, okay? There's reversible and irreversible processes, which is where we're getting to. And then we do system C. A mass suspended by a cable at elevation Z falls when released, as illustrated in 5.1c. So we're hot, let's say 20 feet high. We drop it. and it lands, right? When it comes to a rest, the potential energy of the mass in its initial condition appears as an increase in the internal energy of the mass and its surroundings in accordance with the conservation of energy principle. So, what it's saying is that this mass, when it falls, it lands and it transfers its energy, right? Its potential, when it lands, it transfers its energy into the surroundings, like this plate or whatever it's falling on, okay? And the air, too, transfers it there as well. And then it says, eventually, the mass also comes to a temperature of its much larger surroundings. The inverse process would not take place spontaneously, even though the energy could be conserved. The mass would not return spontaneously to its initial elevation, while its internal energy or that of its surroundings decreases. So, this is the inverse. The inverse is, do you guys think it is possible? Now, we're talking about energy, right? This now has higher energy, right? Do you think it is possible for that the mass to go all the way back up to its initial height while taking energy back in? Like, it is now, the energy that it has landed on is now going back into the mass and going back up. Does that seem plausible to you? Yeah, it does not seem plausible. It does not seem like something that we can do, right? It does not work that way. So, these are just the three major examples, right? And so we're going to talk about this. It says, in each case considered, the initial condition of the system can be restored, but not in a spontaneous process. Some auxiliary devices would be required. By such auxiliary means, the object could be reheated to its initial temperature, the air could be returned to the tank, and the mass could be lifted to its initial height. Also, in each case, a fuel or electrical input would normally be required. So a permanent change in the conditions of the surrounding would be the result. So what it is saying is that we could get this mass back up, right? Like, we could hook this to a pulley and we could pull this back up to its initial height. But the system has now changed, right? Because we dropped it here. Right? We dropped the weight. This is the system, this big circle. We dropped the weight. Inside of this system, we have, energy transfer from the mass here down to there. But to get it back to its initial height, we would have to input something right here, which would be like some sort of work, right? Some energy we would have to put in. There's no way, it doesn't just float back up to its initial height. And so the point is that this system would have to be altered. It would have to be changed from the initial, right? Something would have to be done in order for it to go back in or go back up. So, like, for example, the air one, it flows out, and for something to get it to go back into the can or the whatever this is, the container, something else would have to occur. That would have to be an input, same as the temperature. And it doesn't occur spontaneously. It's like a process, right? It doesn't just happen. Like, as soon as you open this, it goes out and the energy is transferred. It would have to go, it would be, steps back to the other way. So essentially, one happens instantaneously, right? And one of them doesn't. One of them happens with so one is spontaneously, which just happens immediately. The other one is not spontaneous, right? It happens with it's like there's something direct that happened to add that to it. Like, we had to put something in to get it back to the top, or the pressure in, or the temperature high. So it's not spontaneous, and that's where we're getting here. So it said, the foregoing discussion indicates that not every process consistent with principles of energy conservation can occur. Generally, an energy balance alone neither enables that preferred direction to be predicted, nor permits the processes that can occur to be distinguished from those that cannot. In elementary cases, such as the ones considered in the previous example, experience can be drawn upon to deduce whether particular spontaneous processes can occur and to deduce their directions. For more complex cases where experience is lacking or uncertain, a guiding principle is necessary. This is provided by the second law of thermodynamics. It says the foregoing discussion also indicates that when left alone, systems tend to undergo spontaneous changes until a condition of equilibrium is achieved, both internally and with their surroundings. In some cases, equilibrium is reached quickly, and in others, it is achieved slowly. For example, some chemical reactions reach equilibrium in fractions of seconds, and an ice cube requires several minutes to melt. and it may take years for an iron bar to rust away. Whether the process is rapid or slow, it must of course satisfy conservation of energy. However, that alone would be insufficient for determining the final equilibrium state. Another general principle is required. This is provided by the second law. So the ice cube example is a really good one. So if you drop a piece of ice cube on a hot counter, right? Or if you drop an ice cube on the counter, the ice cube will eventually melt, and then the water will then obviously change phase. It will now become liquid phase, and it won't go back the other way. That is a process that doesn't go back the other way unless we take some heat out, right? Unless we cool it down. It doesn't go back the other way. If you keep the ice on the counter, the energy doesn't from the counter go back into the ice and make it an ice cube, right? I think we all can agree on that. And so that is where we're talking about here. Essentially, we are talking about processes that can occur or can't occur. And the conservation of energy doesn't tell us that. The conservation of energy principle just tells us how much energy was transferred, right? We have Q minus W is equal to, H1 minus H2, right? Or something like this. But it does not tell us, while there is a conservation of energy, it doesn't tell us if it's possible or not, right? Just because, for example, if we did the reverse of the ice cube, and we said that we just said that there was some heat leaving, some heat going to this, there would be numbers here. There would be internal energy changes of the ice and the surrounding areas. There'd be changes, but we don't know if it's actually possible or not. The second law provides that for us. It tells us whether it's possible. So here we go. It says opportunities for developing work. So it says, by exploiting the spontaneous process shown in Figure 5.1, it is possible in principle for work to be developed as equilibrium is attained. So here we go. For example, instead of permitting the body of Figure 1a to cool spontaneously with no other result, energy could be delivered by heat transfer to a system undergoing a power cycle. That would develop a net amount of work. Once the object attained equilibrium with the surroundings, the process would cease. Although there's an opportunity for developing work in this case, the opportunity would be wasted if the body were permitted to cool without developing any work. So let me go ahead and draw this. So these are going to be bad drawings, just letting you know. So this is the container, right? This is the hot water container, right? And this was the direction of the first one. So hot water container, right? All of a sudden it now has a circular bottom. And then over here, we go to the last one. So the last one is, this is the 3 steps that it showed in the section above us. So this was the hot, this is heat leaving, and this over here was when T1 equals T naught, right? So this is the point. The point is that you could do something here, right? If you know this is really high temperature, you could use this heat, right? Instead of letting it just, heat transfer out, you could use this, correct? This heat could be used for something. And that is what they are saying, is that it could be used for something. You could take this heat, instead of it, just going to the atmosphere, you could use this heat to heat up something else, right? Instead of just letting it go. And so that is what we're talking about in this right here, which is why it's opportunities for developing work. So this is opportunities for developing work. And similarly, in the next example, instead of permitting the air to expand aimlessly into the lower pressure surroundings, the stream could be passed through a turbine and work could be developed. Now, you would agree, if you use compressed air or something, you wouldn't get a whole lot out of that turbine, right? You could maybe charge a phone for a couple seconds or something, right? If we have pressure container here, right? This is what they're talking about. They're talking about pressure container here, and up here, let's say we have a little turbine, it comes out here and it spins a little blade, right? I don't know. It's going to be a bad drawing either way, so understand that. This is like a pinwheel or something, okay? So it spins this at the top. Yes, and this could be used to generate electricity. Not very much, but this is opportunities for developing work. This is ways that work can be, factored into the equation. So that is what we're talking about. All right, and then in the last one, we don't really need to talk about that one. I think hopefully you guys kind of understand like where we're getting at here. So it says these considerations can be summarized by noting that when an imbalance exists between two systems, there is an opportunity for developing work that would be irrevocably lost if the systems were allowed to come into equilibrium in an uncontrolled way. Recognizing this possibility for work, we can pose two questions. The first one, what is the theoretical maximum value for work that can be obtained? So this right here is what we want to focus on. We want to focus on these two. Because these are very important for power generation, right? Essentially, knowing that there are two, knowing there's a temperature difference, right, between two bodies, there is a theoretical amount of work that you could create from those. There is. And that is what we are going to talk about, is that knowing some conditions, you know that there is a theoretical amount of work, and then how does your cycle compare to the theoretical amount, the maximum we could ever achieve. Okay? And so the first one was the theoretical maximum value for work that can be obtained, and the second one, what are the factors that would preclude the realization of the maximum value? So the important part is here. If we find the maximum value, and let's say our cycle, we're trying to compare our cycle to what the maximum value is, we then find the maximum value and we go, okay, so the maximum value is like, let's say the maximum value for work is 100, right? 100 whatever. Then we start to look at what are the reasons why we couldn't get to that. Like, is there some heat leaving the cycle? Are the turbines not properly spinning? Like, is there too much friction loss? We could find ways to get us closer to the maximum value. Tiny changes that help us keep all the energy in the system and being changed to something else that we want. Okay? Have I lost anybody here yet? Type in the chat if you kind of see what we're doing here. Because this chapter is generally very difficult for most people. So I do want to make sure that we are hitting it good, because it is generally difficult for a lot of people, because it's kind of a weird chapter in a lot of ways. But all right, and it says that there should be a maximum value in fully in accord with experience. For if it were possible to develop unlimited work, few concerns would ever be voiced over our dwindling fossil fuel supplies. So that is true. Also in accord with experience, it is the idea that even the best devices would be subject to factors such as friction that would preclude the attainment of theoretical maximum work. The second law of thermodynamics provides the means for determining the theoretical maximum and evaluating quantitatively the factors that preclude attaining the maximum. So here we go. Aspects of the second law. We conclude our introduction to the second law by observing that the second law and deductions from it have many important uses, including means for predicting the direction of the process, establishing conditions for equilibrium, determining the best theoretical performance of cycles, engines, and other things, evaluating quantitatively the factors that preclude the attainment of the best theoretical performance. So what is stopping us from getting to the best, getting to the highest level? What is stopping us? Dr. Matthias, who teaches the other class, used to use this example. He used to go, everybody in here has the potential to get 100% on the exam, but most of you won't, right? And so he used to say that it's the potential to get it 100%, but you have to understand the factors that preclude you from getting it 100%. So did you study? Did you pay attention in class? It's bad uses of energy is what he used to say. Is that bad uses of your energy gets you to become inefficient in how you should be studying for Thermo 1. And so these are ways that get you not getting 100%. So hopefully that makes sense. And hopefully doesn't depress you too much. So other uses of the second law include defining a temperature scale independent of the properties of any thermometric substance, developing means for evaluating properties such as U and H in terms of properties that are more readily obtained experimentally. Scientists and engineers have found additional uses of the second law and deductions from it, It has also been used in philosophy, economics, and other disciplines far removed from engineering thermodynamics. It says the 6 points listed can be thought of as aspects of the second law of thermodynamics and not independent and unrelated ideas. Nonetheless, given the variety of these topic areas, it is easy to understand why is there no single statement of the second law that brings out each one clearly. There are several alternative yet equivalent formulations of the second law. In the next section, the 3 statements of the second law are introduced as points, driver available, as points of departure from our study of the second law and its consequences. Although the exact relationship of these particular formulations to each of the second law aspects listed above may not be immediately apparent, and all aspects listed can be obtained by deduction from these formulations or their corollaries. It is important to add that in every instance where a consequence of the second law has been tested directly or indirectly by experiment, it has been unfailingly verified. So essentially this is, it is very well proven. Accordingly, the basis of the second law of thermodynamics, like every other physical law, is experimental evidence. Alright, so then we have statements of the second law. So this right here, the Clausius statement, which we'll talk about in a second, is probably the most, is the one that we study the most in this class. It's one that I have heard a lot of ever since being in it. So it says 3 alternative statements of the second law of thermodynamics are given in this section. They are the Clausius, Kelvin-Planck statement, and entropy statements. The Clausius and Kelvin-Planck statements are traditional formulations of the second law. You have likely encountered them before in an introductory physics course. Probably not. I did not. Although the Clausius statement is in more accord with experience and thus easier to accept, the Kelvin-Planck statement provides a more effective means for bringing out second law deductions related to thermodynamic cycles that are the focus of the current chapter. The Kelvin-Planck statement also underlies the entropy statement, which is the most effective form of the second law for an extremely wide range of engineering applications. The entropy statement is the focus of chapter 6, so that is the next chapter. But for this one, we're going to talk about the Clausius statement and the second law. So it says, the Clausius statement of the second law asserts the following. It is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler body to a hotter body. So what does that mean, right? What does that mean? It's basically what we talked about just before, right? If we have, this is a cold temperature, and this is a hot temperature up here, right? Heat transfer does not work in this direction, right? Would you guys agree? Would you guys agree with that? That it does not, energy transfer from a heat, it does not go that way. It doesn't go from a cooler to a hotter body. It goes from the hotter to the colder, right? And so, that is what that basically meant. And now it said, but the sole, right here, so this is the important one, in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. So the sole result, and that is the important part, because there could be something else in here, right? You could insert some work, right? You could insert some heat. But the sole result, that is the important part of that, is that essentially it's saying, while this right here, ready? This, not possible, right? This is possible. Because now we have something else, right? We've inserted heat. We could get it to the hot temperature. But that's why that sole result is so important. Because that sole result, this Q doesn't exist. And so the sole result would just be from Tc to Th, and it doesn't happen that way. It cannot happen that way. So that is why it said the sole result. And now this right here tells you that it is possible, right? You can insert some work, you can put some heat in, and you will get to the hot temperature. So let's continue reading from there. So it says, the Clausius statement does not rule out the possibility of transferring energy by heat from a cooler body to a hotter body, for this is exactly what refrigerators and heat pumps accomplish. This is exactly what they do. However, as the word sole result, as I said, in the statement suggests, when a heat transfer from a cooler body to a hotter body occurs, there must be other effects within the system. There must be something else happening, right? This isn't magic, It might seem like that sometimes, but it is not magic, I promise you. There's no cards up my sleeves. So, something else has to happen. There has to be some work, has to be some heat implemented in it somewhere. And then it says, if the system operates in a thermodynamic cycle, its initial state is restored after each cycle, so the only place that must be examined for such other effects is its surroundings. Oh, let's get rid of this. And then it says, for example, cooling of food is most commonly accomplished by refrigerators, driven by electric motors requiring power from their surroundings to operate. The Clausius statement implies that it is impossible to construct a refrigeration cycle that operates without a power input. Think about it. Could you cool your food in your refrigerator if there was nothing going into it? No other energy. It has to be cold, so we need to get it cold. There's a lot more thought. There's like thought experiments in this chapter. Right? And so that's what it is saying, is that it cannot happen. Now you might say, oh, well, what if we put ice in there? Well, ice is coming from somewhere else, right? We had to get the ice to be cold, so there is energy involved in that. And we had to put it in the system, so we put some work in to get it in there. We had to lift it in. So the point is that it cannot happen. Something else has to be put in. And that's the point I'm trying to, smack into your heads if it hasn't been made common yet. So, now we have 522, the Kelvin-Planck statement of the second law. So this is the second one, the second part of it. The first one was the Clausius, the second is the Kelvin-Planck. Before giving the Kelvin-Planck statement of the second law, the concept of a thermal reservoir is introduced. A thermal reservoir, or simply a reservoir, is a special kind of system that always remains at constant temperature even though the energy is added or removed by heat transfer. A reservoir is an idealization, of course, but such a system can be approximated in a number of ways. And this is one that I have used. I've told you guys about thermal reservoirs for power plants. It's right here. Large bodies of water, right? That is one. So you guys might say, oh, well, when the power plant expels heat out of the condenser into the hot water, right? It goes hot water out into the lake. You guys might say, oh, well, it's hot, right? So, but the thing is that is there enough of it going out that is going to change such a massive body of water to a super high enough temperature to really affect the intake? Probably not. And so it is an idealized version. Of course, it does change by a little bit, but the temperature is they keep it. It's basically constant in name, right? They say, oh, well, it's always coming in at this temperature. So here we go. Now it says, a reservoir is idealization, of course, but such a system can be approximated a number of ways: by the Earth's atmosphere, large bodies of water, a large block of copper, and a system consisting of two phases at a specified pressure. The most common ones that we will see are this right here. Extensive properties of a thermal reservoir, such as internal energy, can change in interactions with other systems, even though the reservoir temperature remains constant. Having introduced the thermal reservoir concept, we give the Kelvin-Planck statement. Here we go. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. All right, so let's explain this really fast. What does that mean? It's right here in this picture, but this picture's kind of weird, but we'll go over it. So right here, this is the thermal reservoir, right here. Do you think it is possible, if I have, here, I'll just ask a question. Do you think it is possible for me to make work if I have, let's say, I don't know, 500 degree water, and after the process, it's still 500 degrees? Is that possible? Because remember, there's only one reservoir. The only temperature in the cycle is 500 degrees. Nothing changes afterward. Yes, it has to lose something. And so, because remember, if you look at a turbine, right? Remember, this is how these are being approximated. Work is equal to H1 minus H2, right? So if water, because remember, let's say it keeps the same temperature and pressure. If water stays at 500 degrees C before and after the process, these two would be the same, which means work would be 0, right? So the point is that from a single thermal reservoir, you cannot produce work, is what it is saying. You cannot produce any work from a single thermal reservoir, or any meaningful amount of work, right? So, now obviously, I'm sure there's like, well, I mean, I guess even then it'd be different. So, anyway, so it says, the Kelvin-Planck statement does not rule out the possibility of a system developing a net amount of work from a heat transfer drawn from a single reservoir. It only denies this possibility if the system undergoes a thermodynamic cycle. Okay? So in a thermodynamic cycle, so that would be it has to come back to the initial one, right? It has to come all the way back. So like I said, T1 has to equal T2, and which then equals T1, right, in a circle. It has to be there in a cycle. So essentially, it can't. It's not possible in a thermodynamic cycle, which is what we are talking about. But it doesn't rule out such things like, you're below, like, for example, like a windmill, or not a windmill, a wind turbine, right? It doesn't. You make work from a wind turbine, and you have an air reservoir probably at some temperature, and then afterward it's probably a little bit different. But it's not a cycle. Would you agree? But a thermodynamic cycle has to have two separate thermal reservoirs. So, here we go. It says the Kelvin-Planck statement can be expressed analytically to develop this. Let us study a system undergoing a cycle while exchanging energy by heat transfer with a single reservoir as shown by the adjacent figure. The first and second laws each impose constraints. A constraint is imposed by the first law on the net work and the heat transfer between the system and its surroundings. According to the cycle energy balance, you would have work cycle is equal to Q cycle. In words, the net work done by or on the system undergoing the cycle equals the net heat transfer to or from the system. Although the cycle energy balance allows the net work to be positive or negative, the second law imposes a constraint as considered next. According to the Kelvin-Planck statement, a system undergoing a cycle while communicating thermally with a single reservoir cannot deliver a net amount of work to its surroundings. The net work of the cycle cannot be positive. However, the Kelvin-Planck statement does not rule out the possibility that there is a net work transfer of energy to the system during the cycle, or that the net work is 0. Thus, the analytical form of the Kelvin-Planck statement is the following. Work cycle is less than or equal to 0 for a single reservoir, as we have stated before. Where the words single reservoir are added to emphasize that the system communicates thermally only with a single reservoir as it executes the cycle. In section 5.4, we associate the less than or and equal to signs with the presence and absence of internal irreversibilities, respectively. We'll get to reversibilities soon. The concept of irreversibilities is considered in the next section. The equivalence of the Clausius and Kelvin-Planck statements can be demonstrated by showing that the violation of each statement implies that the violation of the others. So then we have entropy statement, although let me see what time we've got and where we're supposed to be today. So Wednesday, nope, no, we're right down here. 5152. Okay, so we got some time. All right, so it says 5.2.3, which is entropy statement of the second law. Mass and energy are familiar examples of extensive properties of systems. Entropy is another important extensive property. We show how entropy is evaluated and applied just for engineering analysis in Chapter 6. Here we introduce several important aspects. Just as mass and energy are accounted for by mass and energy balances, respectively, entropy is accounted for by an entropy balance. In other words, the entropy balance states, change in the amount of entropy contained within the system during some time interval is equal to the amount of entropy transferred in, across the boundary of the system, plus the amount of entropy produced during the system's like processes, right? So this one's different. It's not like, minus the other one, right? This one is entropy transferred in across the system during the time interval and add, essentially. But this one right here, I think, ends up being delta S as well. But we'll see. Like mass and energy, entropy can be transferred across the system boundary. For closed systems, there is a single means of entropy transfer, namely entropy transfer accompanying heat transfer. For control volumes, entropy is also transferred in and out by streams of matter. The entropy transfers are considered further in Chapter 6. And it says, unlike mass and energy which are conserved, entropy is produced or generated within systems whenever non-idealities, or called irreversibilities, such as friction, are present. The entropy statement of the second law states it is impossible for any system to operate in a way that entropy is destroyed. Okay? It says it follows that the entropy production term may be positive or zero, but never negative. Okay? Thus, entropy production is an indicator of whether a process is possible or impossible. So let's go through that again. And so this part right here, entropy produced, which ends up being this variable, it ends up being like sig. I think this is a sig. It's not a sigma, is it? Somebody let me know if that's right. But it ends up being that. I'll try and get a better one, but I'm like really bad at this. It ends up being that. And so entropy produced has to be greater than or equal to 0. It cannot be negative. Does that make sense? And if you get a negative entropy produced, it means that your cycle is impossible and cannot happen. So these will be questions you end up doing, by the way. These types of questions, you will be given a cycle that operates between some thermal reservoirs, and you will have to find entropies, and you will have to tell me if it is possible or not. Something like that. That is a common question for this chapter. All right, let's get rid of that arrow and then finish this up today. So it says, second law summary. In the remainder of this chapter, we apply the Kelvin-Planck statement to the second law to draw conclusions about systems undergoing thermodynamic cycles. The chapter concludes with a discussion of the Clausius inequality, which provides the basis for developing the entropy concept in Chapter 6. This is a traditional approach to the second law in engineering thermodynamics. However, the order can be reversed, namely the entropy statement can be adopted as the starting point for the study of the second law aspects of these systems. So we are going to stop here for today. Before we go, are there any questions with what we've done so far? This chapter, like I said, has a tendency to be rather difficult for people because it's a lot of conceptual things, right? It's a lot of, is this cycle possible? What is reversible? What is an irreversibility? Things like that. Did it make sense in some way? I hope. So the major things I would want to take away is that work cannot be created from a single thermal reservoir in a thermodynamic cycle, right? That's one thing I would take away, which is this first part, although I do this every time because I cannot control my mouse. Over here, cycles like this things like this cannot happen unless the reverse process cannot happen unless we input something in, which is essentially what I just said, right? Something else has to happen before. And then, another things, theoretical maximum values and what is stopping us from reaching it are things that you will be asked conceptual questions on. Like, for example, why isn't this value the same as the maximum value? And you will have to tell me what is stopping us. Like, why did we not get there? Okay? And then, obviously, the Clausius and the Kelvin-Planck statement, which is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. So that is the first one. Essentially, the first one has to do with heat transfer. The second one has to do with work. So the first one states, the Clausius statement states that you cannot go the reverse. You can't go cooler to hotter without something else happening in between, with some other result or something else have to happen. And then the other one, the work one, is also very similar. It says that you cannot create work leaving the system. Like, you cannot send work out of the system from a single thermal reservoir. If you have 500 degree some odd pressure water and it goes through the process and it doesn't change temperature, you cannot make work. There's nothing happening, essentially. So does that make sense? Although I just thought of something that maybe it doesn't break it, but maybe there's a reason why it doesn't work. So does this make sense? Is everybody somewhat good? Your homework, the one that was given last week, is due today, and your homework that was given this week is due Sunday. So hopefully you guys have worked on that. And as to your exams, they will be graded by this Friday, more than likely. So you guys will have them back in your possession, and you guys can ask me. So how it's going to work is, since we haven't done exams this class yet, how it's going to work is I'm going to release the scores to all of you. You guys will see your scores. And from your scores, you guys can then ask me. Like, if you have a question as to why your score was this one way or this another way, you ask me, and you can join me in here. I can send you back a copy of it. Like, I can send you the graded copy. You join me in here, and we can go over it, like why you did this wrong, or, why was this right? Something like that. So if there's no more questions, I'm going to go ahead and take attendance, and you guys are free to go. Let me go ahead and stop the old recording.